저는 이제 여러분들한테 대부분 알고 있겠지만은 공지사항을 하나 알려주도록 하겠습니다. 우선 음, 지금 역시 코로나19의 확산이 아직 진정세가 잡히지가 않아서 국가 차원에서도 그렇고 또 거기에 발맞춰서 학교 차원에서도 온라인 강의를 2주 더 연장하기로 되어 있습니다. 해야 있습니다. 그래서 많은 학생들이 이미 여기에 대해서 공지를 받았을 거로 생각을 하고요. 그래서 원래 계획상으로는 오늘이 마지막 온라인 강의가 되었어야 하지만 이제 마지막 강의가 되었어야 되지만 2주 더 연기를 해서 4월 11일주까지, 그래서 오프라인은 4월 13일 월요일 날 일단 우리 대면 강의를 그때 시작하는 걸로 일단 그렇게 계획을 변경을 하도록 하겠습니다. 음. 자, 반갑습니다. 자, 그래서 어, 이 국가 차원에서 어쨌든 모두의 안전을 위해서 수행하는 조치인 만큼 일단 2주 더 국가의 정책에 그대로 따르는 형태로 어, 강의를 계속해서 일단 온라인 강의로 진행을 하도록 하겠습니다. 자, 그러면 오늘 지난 시간에 했던 내용들을 따라서 뒷부분에 이제 오늘 강의 내용을 시작을 하도록 하겠습니다. So, last time, chapter 5, reactor kinetics. So, last time we started our study on reactor kinetics, and after introduction, we derived neutron balance equation. So, from as always, the neutron population depends on three different factors: location, energy, and time. And this time we are going to focus on the factor time, and then simply assumes that we are going to take average on energy and space. So from neutron balance equation, so let's briefly review what we studied last time. So from neutron balance equation, we assume infinite medium to ignore the dependency on space, and also take average on all energies. So by doing that, we could derive this type of equation. This is for non-multiplying systems. That means we ignored the fission. And we covered so we covered infinite medium non-multiplying systems, and after that infinite medium multiplying systems, which includes the fission term. And then we now we then, instead of infinite medium, we started to consider finite medium multiplying systems. So for doing that, we introduced here the leakage term. So we basically introduced the leakage term, and we assumed that the number of neutrons leaking out of the system, or leaking out of the reactor, is proportional to the number of neutrons observed. So in that sense, we could derive such relation, and then we arrived at equation 5.22. So we only have one independent parameter, that is T. So n neutron density and the source, they are all only functions of one parameter, time. So in that way, we focus on the dependency of a neutron population as a function of time. So the change of neutron equals the number of neutrons from external neutron source plus this factor, which is related to or what is that? Macroscopic fission cross section, and L is also related to neutron lifetime. So with this equation, it is expected that we will be able to calculate the change of neutrons as a function of time. So you may see figure 5.1. So it tells us that when k equals 1, so basically two different cases. The first case is that first we are going to set st to 0. That means we are going to ignore the external neutron source. So for the case when we do not have any external neutron source, so that's the case of A in figure 5.1. So that is when we do not have any external neutron source. So in that case, when k equals 1, the neutron density will maintain its value. When k is bigger than 1, exponentially increases, and when k is smaller than 1, it gradually decreases. So the three states are called as critical state, supercritical state, and subcritical state. So this is the case when we do not have any external source, when st becomes 0. And of course, I think u, because k is a constant and L is also another constant, so it is not very difficult for you to derive this equation. It is simply exponential form. So I hope most of you do not have any difficulty in deriving equation 5.24. And also, once again, when k is bigger than 1 or equals 1 or smaller than 1, they are called as supercritical, critical, and subcritical states respectively. So the second case is where time independent source is present. So that means st is not 0. st is not 0, and of course one of most simplest case would be when st is a constant. So when st becomes s0, so in that case the equation would be simply inserting s0 here. So then we solve the differential equation by introducing integration factor, and we will be able to find the solution just like this one. So I hope most of you do not have any difficulty in solving this type of differential equation, the use of integration factor. So, so far we with this. Let's see. In case of when k is bigger than 1, so just think about that. When k is bigger than 1, then of course this exponential term, it gradually, as we can see in figure 5.1 and b, of course this is the case when source is present. And what you can see is that the neutron population will gradually increase, exponentially increase. What if k is smaller than 1? When k is smaller than 1, then it gradually increases but eventually approaches to some steady state value. So, of course, later we are going to derive the equation for k equals 1. So, when we talk about time independent or steady state neutron density, then it can be derived by two different cases. So let's see. Of course, the next page. Let's first see the case when the solution for k is smaller than 1. Then, when k is smaller than 1, then maybe the solution, basically the solution is the same, but it is written in a different form here. So previously, when k is bigger than 1, so when k is bigger than 1, so in our previous solution, so when k is smaller than 1, we simply, so instead of k minus 1, we placed it as 1 minus k. I mean, when this is the solution, equation 5.26 is the solution for when k is bigger than 1. And of course, when k is smaller than 1, the solution is exactly the same, but we are going to simply change its form. So we are going to change, instead of k minus 1, we are going to place it as 1 minus k. And also, instead of exponential minus 1, we replace the order so that it can become 1 minus exponential. And that's the form that we can find in equation 5.27. So basically the two equations are equivalent to each other, but it looks more straightforward for us to see that in this is the solution for k is smaller than 1. And also in the part of exponential, instead of k minus 1, it is replaced with 1 minus and 1 minus, open the parenthesis, and 1 minus k. So the two equations, once again, two equations, 5.26 and 27, they are completely, exactly same equations, but they have slightly different forms to give us more intuitive way of understanding the final calculation result. So these are what we could find in the case, so the case of supercritical condition and subcritical condition. And here what is important is that in this case we have a time independent solution. that means neutron density maintains its steady state value. And that is the solution is that when exponential term decays out, and only this part will remain. So the time independent solution is that L S0 minus 1 minus K. So the point is that, let's see. So let's go back to figure 5.1. So 5.1. So when there are two cases, then time independent, that means a steady state solution for neutron density are possible. The first case is that when there is no neutron source, then K equals 1. And the second case is that when neutron source is present, then when K is smaller than 1. There are that two cases, only that two cases we are going to have a time independent solution for neutron density. So we just covered the we just covered when there is no external source, supercritical, critical, and subcritical states. And when external source present, we just covered the supercritical and subcritical state. And what about the case when the criticality is maintained? So they can be found in this part of our text. This is the case when K equals 1. So it tries to derive the equation. So instead of replacing K equals 1, so in such case K minus 1 becomes 0. That is not favorable in the viewpoint of mathematics. So it takes a limit when K approaches 1. And exponential part is expanded with a power series. And then K minus 1, K minus cancels. So this K minus 1 and 1 K minus 1 here will cancel this K minus 1 in the denominator. And then the limit as K approaches to 1 will be S0, and it's going to be, so also L will cancel out, and the final solution will be S0T. So this is the solution given in the textbook. But of course, this can be one solution for you to understand. And of course, with this, you will be able to see that this solution, NT equals S0T, is consistent with other cases, with the solution for other cases that could be found in the previous two equations, 5.26 and 27. And in fact, there is another more easier way to find this solution. So let's so this was the original solution, original equation that derived all these solutions. And then when there exists external source S0 here, And when k equals 1, then the second term will disappear. And then the equation becomes d dt nt equals s0. So solution can be easily found as s0t. So I hope all of you do not have any difficulty in finding that solution. So let's go back to figure 5.1. All these solutions for NT were for explaining this figure 5.1. So when there is no external source and when there is external source, and this is the solution. These are the solutions for the case of the solutions depending on the multiplication factor k. So after understanding all these solutions, of course the textbook also tells us what I just told you. So there are only two situations in which time independent population of neutrons can be established. The first one is that critical system in the absence of external source, so that is k equals 1 and s equals 0. The second case would that the subcritical system with external source, so k is smaller than 1 and s is bigger than 1. S is bigger than 0. So only in such two cases, only in two situations, we are able to have time-independent steady-state solution for neutron population or neutron density. So, what we could observe, what we have seen is that in figure 5.1, the relation is basically, the neutron density basically follow exponential growth or exponential decay. So that means very small deviation from multiplication 1 will result in large change in neutron population because it increases exponentially. And also, this neutron lifetime, which is critical in determining the growth or decay rate of neutron population, this neutron lifetime ranges from 10 to the power minus 8 to 10 to the power minus 4. This is very, very short time. So in just 1 second, the neutron population can increase significantly in less than 1 second. Because in such case, even if we consider neutron lifetime 10 to the power minus 4, in 1 second, there are almost 10,000 new generations. And that can significantly increase neutron population. So in such cases, it is very hard to properly control the reactor power. So it says that so with such a small neutron lifetimes, controlling a nuclear reactor would be very difficult if all the neutrons were born instantaneously with fission. So if we only have such prompt fission neutrons, then it will be very difficult to control the reactor power. Fortunately, we have something called delayed neutrons. Of course, in the next section, we are going to start to talk about that. And these delayed neutrons will greatly decrease the rates of change of neutron population. And so that by the existence of these delayed neutrons, we are able to easily control the reactor power. Not easily, in the neutron power, I mean the reactor power can be manageable. So this is the end of section 5.3. So what we just studied in this section is that, so starting from equation 5.22, starting from here, we solved the equation by dividing the two cases when there is no external neutron source and when there is external neutron source. And we could find the solution for neutron density as functions of time, depending on the value of multiplication factor k. And so one more thing that I would like to add in figure 5.1 is that here is that after a nuclear power plant has been shut down, and then of course they do a lot of refueling and some maintenance works, and when they start up, or after the construction of a nuclear power plant, they need to start the nuclear reaction. Or, as I already told you, after shutdown, nuclear power plant need to be started up. And in such case, of course, some external source will be necessary to initiate the nuclear reaction. And the external source is inserted. And then how the criticality can be determined. Of course, there is some procedures for starting a nuclear reactor, and at some point, what the operators of a nuclear power plant observe is that whether this neutron density gradually increases, and whether the neutron density increases linearly, as you can see in the B of figure 5.1. So if the neutron density increases linearly, then in such case, it can be declared that the nuclear reactor finally achieved the criticality. And of course, after achieving criticality, there are many tests, the so-called reactor physics tests, to be performed. And after that, the reactor operators gradually withdraw control rods, and they gradually increase the reactor power. And then eventually they approaches 100% reactor power. So that is the way a nuclear power plant is started, and then raise the reactor power, and finally arrive at 100% full power of the reactor. So what we can see is that when there is external source, then linear increase indicate the critical state of the reactor. So if I wonder whether students have any question about section 5.3. So if you do not have any questions, then I'm going to move on to section 5.4. That's delayed neutron kinetics. So now, of course, most of fission neutrons, more than 99% of fission neutrons are produced instantaneously. They are called prompt fission neutrons. But there are a very small fraction, denoted as beta. A small fraction of neutrons are produced by fission fragments, some fission products or fission fragments that emits neutron. And these fission products are called as neutron precursors. And there are many such neutron precursors. In other words, there are many neutron emitting fission fragments. And they are usually lumped into 6 groups depending on their half-lives. So figure 5.1 gives us such 6 groups. So we have 6 groups depending on their approximate half-life, and these are simply the fractions of delayed neutrons. That means a very small fraction of neutrons are produced by these neutron emitting fission products. And what are the fractions of such delayed neutrons? In case of uranium 235, it is simply less, just about 0.65%. 0.65%. So in case of uranium 233 and uranium 239, their fractions are much smaller than this. And from the viewpoint of nuclear safety, as this fraction of delayed neutron is bigger, then it is easier, more convenient to properly control the reactor power. That means smaller neutron fraction. So in other words, the nuclear reactor with uranium 233 or plutonium 239, it will be somewhat difficult for us to properly control the reactor compared to those reactors utilizing uranium 235. So these are the fractions of delayed neutrons in 6 groups. And of course, we also in this table we also have a total number of neutrons per fission reactions. That was denoted as nu. So what we can see is that more neutrons are produced when fission reaction occurs from plutonium 239. So with these data, what we are able to do is that first, so beta is the sum of 6 groups, the sum of the fractions in 6 groups. So this beta was, in case of uranium 235, 0.65%. So in each group, let's go back to table 5.1. So in each group, we have fractions. So these are beta 1, beta 2, beta 3, and so on. So we have beta I, and we also have associated half-lives. So this would be T half-life I. So with this beta I and T half-life I, beta I and T half-life I, we will be able to calculate kind of average half-life. Average half-life. And because we know that half-life and decay constant has this relation, so of course this number 0.693 comes from natural log of 2. And then we are able to calculate average decay constant. So we have all beta i's. We have all beta I. And we have all half-lives. And here, in case of uranium 235, we have a beta value here. And with data provided in table 5.1, you will be able to calculate lambda, so the average decay constant from the relation. So I hope you will not have any difficulty in calculating that. And I actually calculated in myself, and what I could find was that so this is the way I calculated it, and the calculated half-life, average half-life is about 9 seconds, and the calculated average decay constant was about 0.07, about 77. So it is in the rate it is close to 0.08. So we need to keep that number in mind. So next page. So previously, when we only talk about probed neutrons, then we use this quantity L, neutron lifetime. And this neutron lifetime is the average lifetime of neutrons. So the average lifetime of neutrons from its birth, from a neutron fission, to its absorption, no matter whether after that by another material or it contributed to another fission reaction. So there must be some average time between fission and the absorption of the neutron. So that time was denoted as L. And in the previous section, I already also told you that this neutron lifetime ranges from 10 to the power, let's see, this lifetime. So that neutron lifetime ranges from 10 to the power minus 8 to 10 to the power minus 4. So that is the neutron lifetime that we are talking about. So let's go back to the page. So also, that is the neutron lifetime for prompt neutrons. And currently we are talking about delayed neutrons. Delayed neutrons. So we may think about average neutron lifetime of delayed neutrons. So of course this would be the time interval between fission reaction and the time the neutron is absorbed or leak out of the system. So that LD, the average delayed neutron time, will be given as first. So think about a fission reaction. Fission reaction occurs. So maybe I would like to, in fact, to make it more intuitive, I would like to change the order of these two terms. So first, first the fission reaction occurs, and some fission products, neutron emitting fission product is produced, and there would be some average time that this so-called neutron precursor or neutron emitting fission products, it is in an unstable condition and then gradually decays out. And there must be some average time from the birth of that fission products, neutron emitting fission products, to its decay. How can you calculate that average time? Average time. So from chapter 1, chapter 1, yes, there must be so that's page 19. So we are going to go to page 19. So something called the mean time to decay. Mean time to decay is given as 1 over lambda. So that is time, the average time that a delayed neutron is produced from its fission fragments or fission products. So first, 1 over lambda is important. So 1 over lambda is the time that neutron is emitted from fission product. So we are going to go back to the page 124. So 1 over lambda is the mean time. Mean time from the fission product, mean time of a delayed neutron is emitted from fission products. Plus, after the neutron is emitted, that it is going to travel through the medium, and eventually it is observed or it leak out of the system or reactor. So that lifetime is denoted as L. So this LD is given as neutron lifetime plus 1 over lambda. And of course this lambda is average decay constant that we could calculate with the data provided in table 5.1. So if we include both prompt and delayed neutrons, then the first part, of course, beta is the fraction of neutrons, the fraction of delayed neutrons. So the beta fraction their average neutron lifetime is LD, and the remaining 1 minus beta fraction will be the fraction for prompt fission neutrons. And in such case, the average neutron lifetime would be L. So if we add the two, then we are going to get 1 L plus beta over lambda. So that is average neutron lifetime, considering both prompt fission neutron and delayed neutrons. And which part, the prompt fission neutron and delayed neutron, which will dominate this average neutron lifetime? So here. So I hope you remember that this L, neutron prompt neutron lifetime, was in the range of 10 to the power minus 8 to minus 4. It's very small number. So compared to that, what about beta? Beta is in the range. So in case of uranium 235, beta is 0.0065. That's what we could see in table 5.1. So this beta value, so let's go back and see once again. Page 1, just 1, 2. Yes, here. This is the beta value for uranium 235. And what about lambda? Lambda was about 0.08. 0.08 or 0.07677. So what kind of value are we going to get if we divide beta divided by lambda, which is 0.0 about 8? So we are going to have a value very close to 0.1. So let's go back. So this would be about 0.1. And L, neutron lifetime for prompt neutrons will be the value less than 10 to the power minus 4. So that means when we calculate average neutron lifetime, this the delayed neutron have this has profound effects. In fact, this delayed neutron lifetime is almost dominated by almost dominated by delayed neutrons. Of course, this does not necessarily mean that the inclusion of or the consideration of delayed neutrons can be performed by replacing L with this L bar. So it's not that simple. We need to establish a set of kinetic equations and solve them to properly address the effect of delayed neutrons. So it says that proper treatment requires a set of differential equations to account for time-dependent behavior of both prompt and delayed neutrons. So from now on, we are going to establish the kinetic equation. And this would be one of the most, I would say, most important equation that you learn in this course of nuclear reactor kinetics and control. So in fact, this figure 5.37 give us another equation, another kinetics equation, which includes the effect of delayed neutrons. So to understand this, to understand what is meant by this, we need to see equation 5.15. So to compare that, okay. So let me write the section, title section. So delayed So I wrote an let's to maintain some consistency with our textbook, let's introduce defining this ST, capital S. So ST is going to be the rate, and this is going to be the ST here. And this is the neutron balance equation. For prompt fission neutrons, for prompt neutrons, that means without considering the effect of delayed neutrons. So this is actually equation 5.15. ST sigma A, and so source, fission neutrons, absorption, and the leakage term. So the effect of delayed neutrons So if you want to consider the effect of delayed neutrons, so first we need to change the term for prompt fission neutrons. So the previous equation is for the case when we do not consider the delayed neutrons. That means all the neutrons. In that case, it is basically assumed that all neutrons are prompt fission neutrons. But because a small fraction of neutrons are delayed neutrons, the fraction of prompt neutrons would be 1 minus beta. So beta here. So source, and this would be this part is for prompt neutrons. And also we need to consider the contribution by delayed neutrons. So plus delayed neutrons, the number of neutrons produced, the number of delayed neutrons produced from neutron emitting fission products would be, so as you can see in equation 5.37, if Ci so if Ci is the concentration of such, and by concentration it means the number of neutrons per unit unit volume. So if this would be the concentration of such fission fragment, such neutron emitting fission fragments, then if we multiply lambda I, we don't have lambda here. So lambda I, this would be one group, this would be the number of neutrons produced by a single group of neutron emitting fission fragments. And if some of them, then this would be all the number of neutrons produced from neutron emitting fission fragments. And of course we need to calculate CIT. And the second, this part would be the number of neutrons observed, and this would be the number of neutrons that leak out of the system. So this is equation 5.37. So once again we introduced beta from figure 5.1 and lambda I. So how can you calculate lambda I? CIT should be something that needs to be calculated. In case of lambda I, we are going to go back to figure 5.1. Not figure, table 5.1. So we have associated half-lives, and of course half-life and the half-life of the group have the relation with the decay constant of the group, lambda I. So lambda I should be calculated with the data shown here. So with this data, we are able to establish this equation. And what about CIT? CIT. So see that, we are going to go back to our textbook. So to calculate CIT, of course, there are 6 groups, and in each group we need to establish this type of a balance equation should be satisfied. So the change in the number of such precursors or neutron emitting fission products is that the number of neutrons, the number of precursors or such fission products are produced minus the number of precursors, the fission fragments, fission products decays out. So what about the production rate? Production rate is that this would be phi. So this would be so phi multiplied with macroscopic fission cross section. That is going to be, so the product of these. So this would be phi. If we multiply this with macroscopic fission cross section, we are going to have fission rate, fission reaction rates. So number of fission reactions per unit time. If we multiply nu, then we are going to have the number of what is that? The number of neutrons, the number of fission neutrons produced. And beta I indicate the fraction of the fraction of each group of delayed neutrons. Of course, we could see those numbers of beta I in table 5.1. So in this, with this, it is going to be the number of fission, the number of delayed neutrons produced per unit time for ice group, and minus for the same group if CIT is the concentration of such a precursor, then lambda I CIT is going to be the number of decays for the fission product. So in each decay, a single neutron will be emitted. So that is going to be the number of neutrons. The number of, because this is the rate of change, the decay rate will decrease as more and more such precursor decays out. So we have this equation should be satisfied for all 6 groups of delayed neutron precursor groups. So basically we have 7 equations. The first one in 5.37. So this is the first equation, first neutron balance equation. And this is the remaining 6 equations are to calculate the number of fission products, or the concentration or density of such fission products. And we need to solve these equations simultaneously. So let's see. Just like So equation, what about equation 5.40? So it has a similarity with equation 5.22. Okay, so when we did not consider the delayed neutrons, this was the solution. And in this case, the difference that we experience is that instead of k, we have 1 minus beta. So instead of k, we are going to have 1 minus beta in front of k. And this term is newly introduced for delayed neutrons. So this one becomes equation 5.41. That means we follow exactly same routine to calculate, or to same routine for equation 5.22, and then we will arrive at equation 5.40. And and also, and in case of a CIT, let's write it down here. So in case of the equation, and this was the neutron balance equation. So if we rewrite equation 5.39, then what we needed is that we have this multiplied with beta I, well, I'm not able to write I here. Okay, beta I minus lambda I CIT. So for 6, when I is 1, 2, 3, 4, 5, and 6. So once again, so we are going to rewrite this equation by introducing, so once again we are going to divide this. So I hope you still remember this. Absorption cross-section. So in the denominator and numerator. And then, so nu sigma f divided by sigma a. What is this? This would be k. Oh. This would be k. And what is sigma a multiplied with the average speed of neutrons? It is already defined. It was already defined, and that's equation 5.5 in page. So let's go back our text. Go back our textbook, page 117, and that is in fact inverse of L infinity. So it is going to be well, I don't know, I have some difficulty in typing. I mean, inserting some data here. So now it becomes equation 5.41. Maybe we may place k in this place. So now it has exactly the same form with equation 5.41. So after that, we just covered all these equations. And what about steady state solution? So steady state solution means that the change rate, the rate of change becomes 0. So that means dn dt becomes 0, and dci over dt also becomes 0. So in this case, from here we are able to calculate, because all others are constants, we are able to calculate the relation between n and ci. So we have such 6 of these relations. So ci will be expressed in terms of some constants and n, and such ci's will be inserted here, or 6 ci's will be inserted here. Then we are going to have only the equation only with the neutron density, I mean steady state neutron density. So n can be calculated in that way. So or n can be calculated by using equation. So eventually we are going to get this type of equation here. So this is with this we are able to calculate the steady state neutron density or neutron population, and after calculating n, we are able to calculate each of ci. So this is when external source is present, then neutron density will be given in this form. And in the absence of source, when we do not have a neutron source, then of course a steady state condition can only be achieved when the reactor is in the critical state. So these are so I'm going to take a short break from now on, and I also want to check your attendance. So of course later I'm going to check whether that E-class, if you opened this lecture through E-class, then I'm expecting that the system, E-class system, is recording your attendance, but I just as a backup, I want all of you to leave your name in the chatting window so that I can check your attendance. 자, 지금부터 한 15분 정도 휴식을 하고 4시 30분부터 강의를 시작하고요. 그 다음에 출석 체크를 하겠습니다. So, in our first part of today's lecture, we started from section 5.3, and from the neutron balance equation, by solving the neutron balance equation, we calculate what NT will look like. And then, so depending on also the value of multiplication factor k, so when k is bigger than 1, k equals 1, and k is smaller than 1. And then section 5.4, we are currently talking about section 5.4. We introduced the concept of delayed neutrons, and established the neutron balance equation for the case when these delayed neutrons are considered. So we came to this set of equations. So basically there are 7 equations. One for the neutron balance equation, the balance of neutrons, and 6 for the concentration of precursors, neutron emitting fission products. And also when we have time independent steady state solution, that is going to be the N is going to be given in this form. This is when we have external source. When we do not have external source, if S0 equals 0, then when as far as k equals 1, then any value of n will maintain its value. So there are also again 2 different cases that we can have a steady state, that is time independent neutron density solution. So from now on, we are going to introduce a very important concept in this nuclear reactor kinetics, that is reactivity. So this reactivity concept is introduced to describe time dependent behavior. So just previously we talked about the 2 cases when we are going to have time independent solutions. So we are going to introduce reactivity to describe time-dependent behavior. So reactivity is defined as k minus 1 over k. So if we think about the condition of k, when k equals 1, rho becomes 0. That is the case of critical state. When k is bigger than 1, we are going to have this reactivity rho. So when k is bigger than 1, we are going to have rho bigger than 0. And that corresponds to supercritical state. And when k is smaller than 1, we are going to get negative reactivity. So that means subcritical state. And also we are going to introduce prompt generation time, which is denoted as capital of lambda, capital lambda. So it is given as neutron lifetime divided by multiplication factor. So basically, because multiplication factor does not have any dimension, while L, neutron lifetime, have the dimension of time. So this capital lambda also has the dimension of time. So this is why it is called as prompt generation time. So in that case, of course the equation, the neutron balance equations can be now rewritten in this form. So let's so by defining reactivity, so reactivity so let's utilize this. Reactivity is defined as rho equals rho equals k minus 1 over k. That is how reactivity is defined. Reactivity, and also let's introduce prompt generation time. That is so lambda, capital lambda, and L divided by K. So here we have an inverse of prompt generation time. So now let's rewrite this equation. So if we divide both numerator and denominator with k, then of course what we are going to have is, divide the numerator with k, that is going to be, and also L over K will be in the denominator. And minus K. So beta so what we are going to have here is that and I'm going to now change this order, and this is going to be the reactivity, and the denominator we are going to have prompt generation time. So here we have reactivity, and here we have neutron prompt generation time. So that's I'm sorry. So let me just hold. I'm sorry. So we so now we are going we just derived the equation 5.47 here. And also in case of 48, from here only this part will be changed to 1 over prompt generation time. So let me rewrite this here. So instead of that, we just introduced prompt generation time. We don't need this. Instead of that, it is replaced with 1 over prompt generation time. So this is for I 1, 2, 3, 4, 5, and 6. So we just derived 5.48. So let's go back to our textbook. So we just derived the two equations. And so in many cases, K is going to be very close to 1, or vector will be in the critical state. So usually it can be approximated that the capital lambda neutron the prompt generation time. So this prompt generation time is very close to the neutron lifetime. Yeah. So of course we are able to find out their steady state conditions. So by placing the rate of change as 0, and also by placing rate of change as 0. So of course once again the steady state Ci will be given as a function of steady state neutron density. So here the precursor solution will be given in this form. And when we insert this relation into equation 5.47, then we are going to have just one single equation for the steady state neutron density, neutron population. And we will be able to find out the steady state neutron density. So in most systems, let's see. this is much smaller than 1. So previously we calculated lambda over beta. That was that was close to 0.1. That average value was 0.08 or 77. And of course this capital lambda is also, the prompt generation time is also very a small number. So if we multiply all of these, we are going to have a very small number, less than 10 to the power minus 4 minus 5, and much smaller than that. So if we consider that, then Ci will be much bigger than N. The steady state concentration of neutron emitting fission products, the precursors, will be much bigger than neutron density. So this is what it says. So the number of neutron emitting fission products in a reactor is much larger than the number of neutrons. So we just finished section 5.2. So I want 5.4, the section for delayed neutron kinetics. And we defined what reactivity is, and by using it, we rewrote the 7 equations in terms of reactivity and prompt generation time. Of course, we established the equations, and now it is time to simultaneously solve those 7 equations. So I wonder whether any of you have any questions about this. So let's start section 5.5, step reactivity changes. Let's see the equations and step reactivity changes. So if we go back, so first figure 5.2. So this is neutron population following reactivity insertion of 0.1 beta. So if you remember how small beta was 0. In case of uranium 235, beta was 0.65%, and the 10% of it would be also a very small number. But that is usually, the unit, that is the number of that, such numbers are those numbers that we usually deal with in dealing with reactivity. So the beta is going to be kind of important unit in estimating the magnitude of reactivity insertion. And in this case, we inserted 0.1 beta. So that is, so what I'm saying is that reactivity is absolute value will be very, very small. Usually 10 to the power minus 5 is used as a basic unit of measuring the magnitude of reactivity. And in this case, it is 0.1 beta. So, so 0.1 beta. So in that case, that is going to be about 65 multiplied. So let me write that down. So as an example, reactivity insertion 0.10 beta. Zero point 0.10 beta. So, because beta is such a small number, 0.10 multiplied with 0.0065 for uranium 235. So that's 0.00065. That is equivalent to 65 multiplied with 10 to the power minus 5. And no unit is associated with reactivity. So reactivity is just a dimensionless quantity. So what I was told you was that this is a small number. So 0.1 beta is this small number. And when we talk about reactivity, 10 to the power minus 5 is the basic unit that we utilize in dealing with the magnitude of reactivity. And if I'm telling you one more thing, this is called as PCM. This is called as 65 PCM. So PCM indicate percent milli. Percent indicate 10 to the power minus 2. Multiplied with milli indicate 10 to the power minus 3. So it basically indicates 1% of 10 to the power minus 3. So basically 10 to the power minus 5. So in terms of so this was the magnitude of reactivity that is inserted in our example in figure 5.2. So I just explained how big this reactivity was. So if we see the neutron population, what we can see is that if we see this figure 5.2, what we can see is that the neutron population, when reactivity is bigger than 0, this is of course the case for supercritical state, then of course the neutron density increases exponentially. While when we inserted negative reactivity, then the neutron density decreases exponentially. But what we can see here is that there is some change. So if there is some change, some kind of a step change in the magnitude. of, so when we inserted the this reactivity, then so, in a quite short time the power increases like this, and then it follows the exponential function. And also when we inserted the negative reactivity, in a very short time the reactivity, the neutron density suddenly reduced to some value and approaches to and reaches some value, and then follows the exponential decay curve. So these are called as prompt jump. So here we have this word prompt jump. And after prompt jump, then we have exponential growth or decay. And so it says that this prompt jump is abrupt because it is controlled by prompt neutron lifetime, which is in the range of about 5.10 to the power minus 5 second. So it just take effect so suddenly, and then after that it gradually follows exponential growth or exponential decay. So we are going to in analyzing this behavior, we are going to first divide this behavior into two parts. The first, we are going to see this kind of asymptotic exponential growth or exponential decay part first, and after analyzing that we are going to talk about this prompt jump. So in analyzing that asymptotic behavior, this exponential growth or exponential decay behavior, so this asymptotic behavior may be represented as exponential of some time. And we are going to define a new parameter called the reactor period. And this reactor period can be positive or negative. If reactor period is positive, then of course we have a positive exponential function. If reactor period is negative, then we are going to have negative we are going to have exponential decay function. So depending on whether this reactor period was positive or negative, the reactor will be supercritical or subcritical. So from now on we are going to actually try to calculate or trying to find out this reactor period from the 7 simultaneous differential equations that we derived in our previous section 5.4. So how can you derive or find out this reactor period? So let's go back to our note. We define reactor period and T equals So later, mm, t will be given as an inverse of omega. And to solve this equation, we are going to assume solutions. So we are going to assume that this nt, so there must be some insight necessary to find the solution for this. And nt is assumed as a multiplied with the exponential of omega t. Omega t. Of course, that is same with, this would be same with a exponential t over vector period. And in case of CIT, of course, it also has the same form. So BI so also the precursor concentration, the density of neutron emitting fission products will also have this form of solution. So that is what is written in page 127, I mean in the at the bottom of page 127 and at the top of 128. Then, so if we insert these equations, what are we going to have? So let's assume that we do not have any external source. So this was the equation that we had when we do not have external source. And we are going to assume that nt is given in this form. Then if we differentiate nt, then what we are going to have is that instead of nt, we are going to have a omega and exponential omega t. And also in the same way, we are going to have a exponential omega t. Instead of CIT, we have pi exponential omega t. So what we can see here is that all the terms commonly have this exponential omega t term. And of course, they can be cancelled out. So we are going to erase all exponential omega t. So this would be the first equation that we have. What about the remaining 7 equations? So CIT, if we differentiate the CIT, so this is CIT, but if we differentiate this with respect to t, then of course omega will be multiplied here. And also we have NT and CIT. So all the exponential terms, exponential omega t, that is commonly included in all the terms in the left hand side and right hand side, it will be also erased. They also cancels out. Of course, as far as they are not zero, and we know that exponential omega t will not be zero. So now we have the equations 5.49 and 5.50. Of course, one difference is that if we change the order of, if we place omega in front of a and bi, then it will have exactly the same form. So how can you solve the equations? So from here, we are going to solve a bi in terms of a. I'm going to put it by solving. So what are we going to have? We are going to have this term will move to the left hand side. It becomes plus, and it will be included in a parenthesis. And it is going to be, if we move this parenthesis to the right hand side, it is going to be just like this. And yeah, if we move beta I to here, then each bi is given in this form. And we are going to insert this pi to here. Then what we are going to have is that instead of a pi, we have this 1 over lambda is irrelevant to I, so it can be taken out from the sum of so because the summation is performed with respect to I, so we are going to place also lambda I here. So now it has equation 5.51. And after that, we also have this part. So it can be divided into these two parts, and plus. And we are going to calculate this. So it will be same with, so we commonly have 1 over lambda, and also we commonly have a. So this one will be, and in fact a can be, let's see, a can be taken out. So maybe we first erase a first. So if I rewrite it, then so if we delete a in each term, so 1 over lambda will remain here, and minus, so it also have a 1 over lambda, because beta was originally sum of all beta I. So sum of all beta I. And also, instead of sigma, I'm going to use this to be more clear that the summation should be performed for all I. Or maybe I can write it as I equals 1 to 6. So we have this was the second term. So originally it was beta over beta over capital lambda. And if we also one more multiply this here, so I'm going to take parenthesis here and then multiply beta here. Now minus so this beta I lambda I, this minus beta I lambda I will, and also the beta I lambda I here will cancels each other. So only this first part will remain. Omega beta I will remain. So that means what we are going to have, what will remaining here is like this. And if we move omega to here, now we have exactly the same equation shown in figure 5.52. And this equation now rewritten as omega equals, so I'm going to move this one to the left and this one to the right, omega to the right hand side, and reactivity over prompt generation time to the left hand side. Or we can say that we are going to move this term to the left hand side. So what we are going to have is this omega plus omega plus 1 over capital lambda and sum of this term. And if we multiply prompt generation time, capital lambda in each term, it is going to be, so this will disappear, and we are going to have only omega. And this will be same with so this will be same, so omega will be taken out. We are going to have capital lambda plus the sum of all except omega here. So now we arrive at equation 5.53. This is called as in our equation. So this is called as in our equation because the omega, so in the right hand side we have omega, and omega have the unit of inverse of time. So if you remember this equation, t is reactor period, and usually it has the dimension of time and unit of time like a second. And omega also in that case have the dimension of inverse of time. So in the right hand side, omega, because omega have the inverse of time dimension, it is called as in our equation. And of course this prompt generation time has the dimension of time, and also this will have the dimension of time. Beta does not have any dimension, any unit, but omega have the inverse of time, and lambda will have also inverse of time. So the whole part will have the dimension of time, and time multiplied with inverse of time, then we do not have any dimension. That is why this low reactivity does not have any dimension at all. So it is called as in our equation. And this equation, so when rho, the reactivity is given, then by utilizing prompt generation time and beta i's and lambda i's, so omega here and omega here, so it cannot be solved what we call analytically. We cannot solve this by hand. So the solution should be found using some numerical methods. So the finding of a numerical solution is demonstrated in figure 5.3. So if we move back to our textbook, let me Let me take this figure and move this figure to PowerPoint. And we don't need that background figure here. Okay. So this is a figure 5.3. What it tells us is that, let's think about some omega value. Let's write it as, let's draw this line in red color. Okay. So when the right hand side of the equation, let's go back to our textbook, or go back to our notebook. So to find the solution for this, we are going to draw a function. So this will be denoted as, defined as f of omega, a function of omega. And we are going to first draw f omega as, of course, as a function of omega. That is this part. We are going to draw this with as a function of omega. So if we go back to our PowerPoint figure 5.2, this is the figure. And the basic idea is that the solution can be found so this is the right hand side. All these are the right hand side. And when rho is defined, rho is given. So when rho is given, so when some rho is given as some value, then all these will give us the solution for, what is that? The solution for omega. So in this case, so when omega is 0, that is when, I mean, the reactivity is 0, then we are going to have 1, 2, 3, 4, 5, 6, and 7 solutions, 7 omegas that satisfy these 7 simultaneous differential equations. So basically we have 7 solutions of omega. If omega, I mean, if the reactivity is a non-zero value, if omega, I'm sorry, the reactivity rho has a positive value. So if we go back to our notebook once again, if the reactivity has some positive value, now we are going to go back to figure 5.3 again. So if reactivity has some positive value, so all the points, these are the solutions of omega. And if we increase the reactivity a little bit more. So in this case, so we have a 1, 2, 3, 4, 5, 6, and 7 omegas that satisfy the equations. So just like we have two solutions when we solve second order equation, or if we solve what is that? Third order equation, that we are going to have three solutions, just like that. In this case, because after solving 7 differential equations simultaneously, we are going to have 7 solutions that satisfy the equations. So if we go back to our textbook, so that was figure 5.3. And then by drawing a horizontal line for a specific variable rho, that's what I just performed in the PowerPoint, and we are going to have 7 solutions. And of course, depending on their magnitude, we can specify their name as omega 1, omega 2 until it becomes omega 7. And in fact, neutron population has the solution as the sum of 7 ai exponential omega it. So as the sum of all 7 exponential functions will basically give us the exact solution. And as t increases, so if this is the solution for neutron population, so when the reactivity is bigger than 1, well, I could draw a line here. So this is the case when the reactivity is positive. Reactivity is bigger than 0. That is a supercritical state. And of course, the neutron population will increase exponentially in this case. If we see the solutions of this, then we have 1 positive omega and 6 negative omegas. So as t increases, all exponentials of 6 negative omegas will gradually decay out. They will approach to 0. And the solution is basically dominated by the positive solution. So the solution NT can be approximated with just the first one, the first omega. So NT can be given as A multiplied with T over T over reactor period time. In this case, reactor period of time should be defined as an inverse of omega 1. So what I'm writing, so if we write here, the solution can be found that, so NT so basically they have to be, so to be more from I equals 1 to 7, A AI AI exponential I. So for I already told you that we are going to have 7 i's for omega 1, omega 1, omega 2, omega 1, omega 2, omega 7. And what I'm saying is that this is approximated. This is going to be approximated with only the first one, because others will gradually decay out. A1, omega 1. And this will be now rewritten as so maybe you remember that previously we defined reactor period as inverse of omega, where the let's bring so this was the definition of a reactor period, but in fact reactor period is given as the inverse of the biggest omega. So if we go back to our textbook, in fact it tells us that, well, T is given as 1 over omega 1. What if reactivity is a negative value? That is, what if reactivity is a negative value? Here. So maybe this type of negative value. Well, so this is another example. When reactivity is negative, we have 1, 2, 3, 4, 5. I'm sorry, that once again. 1, 2, 3, 4, 5, 6, and 7 solutions. And they all have exponential minus negative value. So the solution is that exponential minus negative omega I and t. And if omega I is bigger, I mean if exponential with in fact a smaller value, so bigger in magnitude, in negative range. So the point is that when exponential minus big negative value multiplied with t, it is going to decay out much faster. So omega 1, omega 2, and omega 7, they will decay out much faster, and omega 1 will last for omega 1 will remain even at the end of t. So even though the reactivity is negative, so all omega i's will be negative, but the asymptotic relation, I mean the NT will be dominated by the biggest omega 1. So still this relation, the reactor period, is defined as the inverse of first omega is still valid, even for negative reactivity. So, with this, in section 5.5, so in section 5.5, so 5.4, we derived these 7 simultaneous differential equations with consideration of delayed neutrons. And in this section 5.5, we actually try to calculate or find out these relations to find out solution that governs this change of neutron density. So by introducing Richter period, and we could derive in our equation. And then I also explained how the solutions for in our equation can be found. We have 7 solutions, and in any case, the biggest omega 1 will dominate the asymptotic behavior. So this is going to be the end of today's lecture. So also I also want to emphasize that today we studied a very important relation in nuclear reactor kinetics, that is in our equation, and how we calculate, how we find the solutions for in our equation, and the definition of Richter period. I hope all of you study once again what we studied today. As always, I strongly recommend you and emphasize that you need to read the textbook yourself and then try to understand what is written there. If you have any questions, please ask questions in our lecture next lecture time, next Monday. So I hope everything will be alright until next Monday, and I'm going to stop here, and we are going to see